All right, there are some properties of these definite integrals, I guess they are, because of the region R specified, that are very analogous to previous integral properties you've seen. So the double integral over R of f plus g is the same as adding up two separate double integrals, integral of f plus integral of g. If you have c as a constant, that can pull in front of the integral. You've seen things like that before in Calc 1. And then if f is always greater than or equal to g for all x, y in the region R, so in other words, the graph of f is above the graph of g, then the double integral of f over that region is greater than or equal to the double integral of g over that region. Let's take a look at the integral from 0 to 3 of the integral from 1 to 2 of x squared y dy dx. And then look at the integral from 0 to 3 of the integral from 1 to 2 of x squared y dx dy. These two questions look very similar. The only difference is whether the dx is written last or the dy is written last. Neither computation is really difficult, but I hope you will see from these two examples we do need to be careful. And these two, punchline here, these two questions will have different final answers. So the swap of that dx versus dy at the end is going to matter. The outer integral corresponds to the outer differential. By differential, I mean like dx or dy. So, for instance, let's take a look at that first one. 0 to 3 is on the outside, and on the outside is dx, right? So this means that we look at x. So dx is on the outside, and then on the outside is 0 to 3. So we look, x will go from 0 to 3, and then dy is on the inside. That's going to correspond to the inner integral symbol, so y is going to go from 1 to 2. In the other integral, dy is on the outside, so y goes from 0 to 3, and then the inner differential is dx, so x is going to go from, well, inner integral, 1 to 2. Okay, so look, think of it more like this. Basically, when you see these double integrals where the numbers are written on both of the double integrals, imagine inserting a set of parentheses, basically. That's all that happened here. And focus on the integral inside parentheses first. Okay, since the integral in parentheses is a dy, so think of y as the variable, then think of x as being constant. I hope that sounds familiar. Sounds just a little bit like partial differentiation. So this is going to work out just fine. So let's just go ahead, take this problem, right? And though we will probably not draw these parentheses in the future, let's just do this now because it's the first time. All that happened was inserting some parentheses. Now take a look at what's inside parentheses. Integral 1 to 2, x squared y dy. Treat y like the variable, treat x like a constant. And that means, so copy the x squared. If x is a constant, x squared is a constant. The y is going to integrate to y squared over 2, and we need to evaluate that at 2 and at 1. So let's go ahead and do that step. So we're looking at x squared, y squared over 2, plugging in y is 2, and then x squared, y squared over 2, plugging in y is 1. Looks like this, right? Subtract. Now this looks a little messy, so before we do any integration, we'll just clean this up. What was this? 4 halves minus 1 half is 3 halves x squared. So skipped a little bit of algebra, but okay, we're now needing to integrate 3 halves x squared dx from 0 to 3. Now this problem looks like one you could give to a student taking Calc 1, right? So 3 halves copied times integrate x squared to be x cubed over 3, evaluate at 3 and at 0. So you get a thing that looks like this. Looks like because we got 0 times whatever, that part's just gone. We end up with 27 over 2. Now the other double integral we were given looked like this. Remember the only difference was instead of ending dy dx, this ends dx dy. We'll go ahead and insert that set of parentheses again. Probably in the future, won't be doing that, but just because this is new, hopefully this is helpful. We'll focus on the integral in the parentheses. Notice that it says dx inside the parentheses, so we'll treat x like the variable, treat y like it's a constant. So that integral would look like this, right? X squared would anti-differentiate to x cubed over 3. Just copy the y because that's just like if there was a 5 there or something. Okay, and then we need to evaluate this at 2 and at 1 for the x values. We'll get a thing that looks like this. Maybe we'll, let's see, was that 8 over 3 minus 1 over 3? So 7 over 3y. And then now we have an integral with respect to y. So y squared over 2 evaluated at 3 and at 0. Looks like that. Let's just clean this up a little bit and get 21 over 2. So notice 27 over 2 versus 21 over 2. Okay, the numbers aren't that different, but they are technically different. So these two integrals will be different. So swapping dx dy versus dy dx is going to matter. Basically, what you should do in these is evaluate the inner integral, right? So the innermost d whatever variable tells you what the variable is, and treat all of the variables you see as constant.